Welcome back to the second day of second week. Today's day is dedicated to the tropical variability. We have 3 1-hour lectures in the morning, followed by a hands-on session in the afternoon. Our first speaker is Professor Daehyun Kim from Seoul National University. He works as an associate professor there. Thank you, Daehyun, for agreeing to give this lecture on modeling the Madden-Julian oscillation history and remaining challenges. Thank you.
Good. Hi, everyone. Hope my voice is clear and my screen is also clear. Good to see you all. And I'm sorry that I won't be able to make it this time, but maybe next time. So I'd like to tell you a story about MJO modeling, mostly the history. And then if I have time, I can also talk about a few remaining challenges. I like history, and I like putting things in context. So this is the result of my effort doing it. Okay, let me start my presentation with this sentence. I'm going to show you several sentences like this in the middle of my presentations. So I guess Xu Guang probably talked a lot about the MJO last week, right?
Shugong gave a lecture on moisture mode.
Yeah. For MJO. So the Madden-Julian oscillation is a unique wave in the tropical atmosphere that affects the global weather climate system. I mean, if there is any question that I don't answer today, you can go to Eric on the first floor, on the first row, and ask him questions. Well, to make it as simple as possible, it's a wave with it's a wave with stormy and wet condition in one part and sunny and dry condition in another part. And its wavelength is about 20,000 kilometers. I mean, it varies with different events, but roughly speaking, and also propagates at around 5 meters per second. With this speed, you can complete a full marathon in 2 hours and 20 minutes. So if you divide wavelength by speed, you get around 45 or 46 days of period. That's basically what MJO is, and it's a nice schematic diagram that people are using. And this is rainfall anomalies. I don't think I have to give a lot of explanations of this animation, but the point is MJO is a special wave that modulate tropical rainfall on very large scale and a specific subseasonal time scale. These are snapshots of those MJO-related rain anomalies for different MJO phases. And then this is a summary a diagram that summarizes what kind of weather climate phenomena that MJO affects or interact with. So you can, whatever you think about, I mean, you have it here. And so IOD, monsoons, tropical cyclones, and so on. Now, I'm going to talk a little bit about how Madden and Julian discovered the MJO. I think it's a very interesting story, and there's actually a paper about this by Madden, Roland Madden. Sorry, I don't have that citation here, but it turns out that the prevailing scientific trends, I'm going to tell you what it is in the next slide, of the time, and some random events led to the discovery of the MJO. So here is a couple of pictures that show Roland Madden and Paul Julian when they were young on the right, when they were relatively old on the left. So to complete the story, you have to go back to like late 50s. There was this year of geophysics, 1957 and 58. And as part of that, radios and observations were expanded in the tropics. And in the meantime, in 1960, NCAR established. And in 1964, the computer, at the time, this was like one of the fastest computers in the world. CDC 6600, it developed and supplied to NCAR. And then 1965, fast Fourier transform algorithm was developed. So with this, spectral analysis of big data was made possible. And in the meantime, in the tropical meteorology, we observed the discovery of QBO, and in 1961, so people realized, oh my God, there's something that whose periodicity is 28 months. I mean, it's really interesting and something that we didn't really expect. So there must be something other in the tropical atmosphere. And in 1966, Matsuno derived a set of solutions to shallow water equations and kind of predicted that there must be these kind of waves in the tropics. And then some of them was confirmed by the follow-up studies, mixed Rossby gravity waves and Kelvin waves through spectral analysis. Okay, that's the scientific trend of the time. And then Madden, he got a master's degree and joined NCAR in 67. And then by coincidence, his roommate was Julian. And Julian was in 1967, Julian was on sabbatical. And next year he came back. And it turned out that Julian was an expert in spectral analysis. And Madden's job at NCAR was handling data from field campaigns. So the two met. What they do, they analyze together 50-day data from a field campaign. I forgot the name of the field campaign, and got some results. And then 1960, Madden went to a conference in Honolulu, tropical meteorology conference, and somebody suggested, oh, hey, there's 10 years of data from Canton Island. Why don't you analyze that 10 years of data? I mean, 50 days is too short. And that's what they did. And they analyzed this 10-year data in 1970 and got this results, which shows there's a very strange spectral peak in upper level and low level zonal wind, power spectrum, and the power spectrum of surface pressure. And that's basically their 1971 paper. Okay. And what they did later is, okay, this is just one place. Why don't we just look at other places in the tropics? And this is their 1972 paper, spectrum of surface pressure in 20 places in the tropics. And they found there are many places in which surface pressure spectrum shows 40 to 50-day period, a peak in 40 to 50-day period. And then they concluded their paper with this sentence. This is from their, I think, the abstract of their 72 paper. Evidence indicates that the oscillation is the result of an eastward movement of large-scale circulation cells oriented in the equatorial plane. And the plot on the left is from their figure paper, a schematic. And that's basically what we are using when we explain MJO to public and when we start our presentations in the conferences. So with very limited data set, they were able to capture very accurately what this oscillation is. Okay, that was the story about the discovery of the MJO. And then, if you look at the number of citations, like MJ 72, Madden-Julian 72, Madden-Julian 71, and then you probably all know Willan and Hendon 04 RMM paper. This is the time series of the number of citation. And it was kind of quiet at the beginning, and it kind of ramps up in mid-80s, and then it kind of stays. And then since mid-20s, it kind of goes up crazy, right? And after making this plot myself, I mean, the data is from Web of Science, I felt very fortunate because I started working on the MJO, I think at the right time, right? I started my PhD in 2003 and then started working on the MJO in 2007. Anyway, so after the discovery, this is how MJO got interest in the scientific community. Well, when you discover something interesting, if you are a modeler, you want to know, I mean, if your model can simulate that phenomenon or not. But at one point, it seemed pretty gloomy, realistic simulations of the MJO. And the global climate models once appeared to be impossible. Let me elaborate on that. So this is mid-80s. By then, we have several years of some satellite observations. This is from a figure from Lau and Chen, 1985. And it is basically showing Hofmüller diagrams of some OLR anomalies. And here, solid means enhanced convection. And they found, okay, this is from 60 degrees east to 60 degrees west, covers part of the Indian Ocean until like to the Eastern Pacific. And you see clearly in almost all years, you see some eastward propagating features in satellite observations. But there must be something going on. I mean, coupled with convection, and modelers wanted to see if their model can simulate this. So on the left, these are the list of modeling studies in the mid-80s, late 80s, and also 90s. I think, to my knowledge, these three papers, Hayashi and Sumi 86, Lau and Lau 86, and Hayashi and Golda 86, they are the earliest modeling paper that I can find. And the figure on the left shows a figure from Hayashi and Sumi, 1986 paper. They ran aquaplaning simulations for just 90 days. And then they found precipitation, organized precipitation is propagating eastward. And we're very excited. And they, of course, they did some further analysis to analyze the structure of this feature and so on. But they thought, okay, they captured this phenomenon called Madden-Julian oscillation, and we're pretty happy with that. That was it. And then in early 90s, the weather and climate community, the atmospheric community altogether, they did this kind of intercomparison project called AMID. So they collected a dozen atmosphere general circulation model, and this is a list of it. And I just highlighted their convection schemes. Three of them, cool scheme, which is not used anymore, but at the time was popular. MCS, moist convective adjustment. No GCM uses MCS like convection scheme anymore again, but at the time, some of them used it, and Arco-Schubert's type scheme. And they prescribed, observed SST for 10 years from 1979 to 1989. You see equatorial SST anomalies here, and then you see here 82, 83 El Nino, 87, 88 El Nino, okay? And then many people did many different analyses, but Slingo et al., 1996, they looked at MJO. So this is a long paper. I recommend anybody, any young scientist who are interested in MJO and MJO modeling to read this paper, because they have put so much thoughts on it. And this one shows the upper level velocity potential power spectrum, just took wave number 1 component. And this is their analysis, pseudo observations. And you see in the eastward propagating part of this domain, you see spectral peak. And then if you look at the other plots, different models, you come up with this conclusion that no model, 0, has successfully captured the dominance of the interseasonal oscillation in observations, okay? And they concluded that with this figure, kind of negative, gloomy conclusion, that an accurate simulation of the interseasonal oscillation may be a demanding test for GCM because it has so many requirements. So specifically, they speculated maybe resolution is not fine enough, maybe convection scheme has biases, maybe the models are bad, they have bad mean bias, and if your mean state has biases, then you probably cannot get any realistic MJO. And of course, this is atmospheric general circulation models. There's no air-sea coupling. Air-sea coupling might be a crucial factor for MJO. So, and they did some analysis with the limited number of models. So here's their attempts to look at the effect of resolution. So on the x-axis, these are 14 different models. What the length of the bar shows interseasonal oscillation strength. So the taller, the better. And then they colored low resolution models in black, high resolution models in white, relatively speaking. But it seems, I mean, resolution doesn't seem to affect MJO or ISO strength. Convection scheme, it seems if you don't use moisture convergence, the good models are not using moisture convergence as their closer for the convection scheme. So maybe that's why they are doing better in simulating MJO. And they also looked at if dynamical core is affecting the simulation, or they also examined this SST precipitation relationship. If it's tighter, maybe the MJO is better. That's one aspect of the mean state, and they found the models that has a good MJO, or interseasonal oscillation variability. Their mean state in their mean state, SST and precipitation has a tight relationship. And recently, a paper was published showing that in CMIP6 model, this is also the case. Anyway, now, of course, if things are this much bad, people try to make it better, and ways of improving MJO simulations were suggested. In mostly single model studies, you use a single model and you do some parameter sensitivity test, make changes to this part and that part of the model, and then see what happens. And if MJO improves, you suspect, oh, that's the thing that matters. But the poor GCM performance persisted. Let me show what I mean. So this is one study, Wang and Schulesinger, 1999. They used one model, their model. I forgot the name of the model, but anyway, they employed 3 different convection schemes. I kind of introduced these 3 in the previous slide: and moist convective adjustment scheme, cool scheme, Arca-Schubert scheme. But the point is that, I mean, in each scheme, there's a way of making convection more sensitive to humidity, environmental humidity or relative humidity, okay? And they did parameter sensitivity test with 3 different convection schemes and found this conclusion. I mean, this result. No matter what convection scheme you use, if you make your convection scheme work only when the environment is humid enough, then you get stronger MJO. So here, I mean, the details doesn't really matter. So here is Arca-Schubert scheme, 4 different experiments. And as the number goes up, convection becomes more sensitive to moisture. And then, you know, I mean, it was A4 convection requires very high relative humidity, then your MJO is strong. With cool scheme, similar. With MCS scheme, it's similar. So it seems we know the secret, right? I mean, it seems pretty easy. You just change your parameter in the convection scheme and make it sensitive to moisture. You will get strong MJO. In the meantime, other studies have suggested, no, I mean, yeah, you have to couple your atmospheric model to ocean model, right? The coupling matters. So this is one example published in the same year, Wallace et al. 1999. They used NASA Goddard GCM. No, to the left, this is lag composite or composite diagram of 200 hectopascal velocity potential. Time goes down. So you see some eastward propagation before this left reference longitude, and then kind of dies quickly. But in the coupled model, if you do the same analysis, this eastward propagating signal kind of continues, right? So, they concluded coupling really matters. And there are other studies that kind of supported this conclusion. Although This is not working in every model. In some models, coupling didn't seem to matter that much, or when you couple the model to ocean model, atmospheric model to ocean model, MJO sometimes degraded. Anyway, now we are in the mid-20s. Everybody knows what CMIP is. This is CMIP 3. I mean, 2 generations back, from CMIP 6, and bunch of models. Gilles and Lin et al. Analyzed CMIP 6 models in terms of MJO and other convectively coupled equatorial waves. This is their one of their plots showing power spectrum of precipitation in the middle of Indian Ocean. And two black lines, solid and dashed, they show observations, and colored lines are different models. And like before, if you remember the Slingo paper, only observations show some peak, pronounced peak here, and no models show peak. And it was very similar. So they concluded, except for one model, a French model, CNRM, the MJO variance in 13 out of 14 models does not come from a pronounced spectral peak. There seems to be no MJO in most of the models still. Okay, CMIP 5, in 2013, next generation model, maybe with the knowledge we have gained, maybe we get a better MJO this time. We'll see. This is another MJO simulation diagnostics, and it's similar to the lag composite diagram that I showed you before. In observations, 2 different observation data sets, MJO is propagating eastward, gain time goes down, and all these other panels are showing model simulations. And again, very easy to see that there's no eastward propagating signal in models except for this one. Again, this French model. Again, only one of the 20 models is, quote, able to simulate a realistic eastward propagation of the MJO. So something must be wrong, right? Couple models, CMIP models are couple models. So RC coupling is enabled by default, right? And it shouldn't be that difficult to make the convection scheme sensitive to environmental humidity. I mean, if you are convection scheme developer, you know, I mean, how to make this happen. So why is it the case? Model developers not reading MJO modeling papers or what? It turns out, I mean, this is CMIP 5 model results, and I mean, I know during this workshop and last week and this week, people have talked about this observed strong coupling between moisture and precipitation. This is showing, the black line is showing observations. Precipitation is a function of column relative humidity, and it shows a pickup maybe with column relative humidity greater than 0.8. And these gray lines are different CMIP 5 models, and it seems many climate models are still not sensitive enough to column relative humidity. They fire convection too early when column is not humid enough. And also, I mean, this is my paper 10 years ago. I used the CMIP 3 and 5 models, and I came up with a metric using model simulation results. I kind of measured the moisture convection coupling in model simulations and correlated it with their MJO performance. And I got pretty good correlation with R squared about 0.56. I mean, this tells me at least, I mean, moisture coupling does matter. I mean, it correlates with positive correlation, correlates with MJO performance, but it doesn't explain everything. There must be something else that affects MJO performance. That was the conclusion that I had. Now, in the meantime, I mean, maybe Shugang covered part of this. And in my opinion, since the early 2000s, substantial progress has been made in understanding the MJO as a moisture mode. And this is an animation that shows you the evolution of column integrated water vapor field, like very lately You can actually see MJO here. I mean, MJO is now page 3. It's passing through Eastern Indian Ocean and developing this big gyre. Anyway, I mean, it's not that surprising. I showed you a plot related to this before, but if you just look at on any day, a snapshot of precipitation and corresponding precipitable water, and it's not difficult to see. You get precipitation when column is wet, right? But it took, I don't know, I mean, it took decades for us as a community to realize this simple fact and how critical this is to many aspects of the tropical atmosphere. And this is originally from Bretton et al. 2004. We found the data set that Bretton et al. Used was kind of dated. There's an updated version of it. And if you use the updated version of it, the relationship between column relative humidity and precipitation changes a little bit. I mean, overall precipitation was too strong in version 5 that Bretton et al. Used, and this is version 7 results. And yeah, precipitation is strongly coupled to the degree of column saturation. And this matters especially to the Madden-Julian oscillation. This is a figure from Yasunaga and Mapes in 2012. The coherence squared between rain and precipitable water, how strongly rain variability and precipitable water variability are coupled. And you can see that immediately the region, the spectral space that pops out in terms of this relationship is the MJO band. So the moisture convection coupling is the strongest in the MJO among all convectively coupled tropical waves. And then many studies, Eric's and others, myself, have contributed to establish this idea of moisture mode dynamics of the MJO. I can give 1 hour seminar about that, but to make things very simple, you start with this moisture wave, very similar to the precipitation wave that I showed at the beginning of my presentation. And we talked about in the past few slides how convection precipitation is strongly coupled with moisture. So you can imagine precipitation wave will have very similar shape with the moisture wave. And then it turns out for the MJO, this precipitation anomalies, when you heat the atmosphere or when you cool the atmosphere with diabatic processes, the tropical atmosphere responds to some extent in a predictable manner, right? Matsuno-Gilles response. And this Matsuno-Gilles response to heating anomalies that moves moisture around. So as a result, you get moistening from these horizontal advective processes to the east of where moisture anomaly was positive, and you get this drying to the west of where the moisture anomaly was positive. So as a result, the next moisture peak will appear here, which means the whole wave will propagate. This is a very simple 1-minute summary of the moisture mode dynamics. And then, of course, we know this budget equation by examining this budget equation using reanalysis and model data set, you can analyze and see which term is contributing the most to the moistening and drying. So collectively, we had this conclusion of MJO is a moisture mode in which the maintenance and propagation of convection can be explained by those of moisture anomalies. Now, this is from my other seminar about MJO theory. I try to put theoretical papers, the studies that developed a simple model, a simplified governing equations, and they solved it analytically or sometimes numerically, and their solution looked like the observed MJO, right? And then there are many different types of theories. Some theories argue suggest MJO is a damped Kelvin wave, it's destabilized by wave cis or frictional boundary convergence, multi-scale interaction, gravity wave interference, and in recent few studies here, they argued MJO is a nonlinear moisture, a Rossby wave. And now I highlighted in yellow the studies that I can call moisture mode theories. So at least some part of their model, the moisture evolution is critical to MJO convection, the evolution of MJO convection. And you can see that, the idea was introduced in mid-90s, but it's actually after mid-20s that this idea kind of flourishes. And in theoretical field, theoreticians, they grab this idea and make it complete, and so on. And this is, if you look at this together with the citation number time series that I showed you before, this kind of matches with this rapid increase in the citation number after mid-2000. So in early 2000, we recognized the importance of moisture in modulating convection, and many different ideas came out of this to explain MJO as some sort of moisture mode. Anyway, I don't have time to explain the details of these theoretical work. But one thing that we have learned, and it seems, I think, have kind of affected this modeling efforts in some notable fashion, is this conclusion. Original gradient of the mean moisture has been shown to be a key factor for realistic MJO simulations. Now, if I go back to this diagram, I told you what drives the eastward propagation of the MJO is this moistening and drying through the Matsuno-Gilles response to the heating anomalies. And then this moistening actually comes from these horizontal advection terms. And this is one of my earlier papers. When you analyze MSE propagation using column integrated moistatic energy budget, this is total MSE tendency. And this is the propagation of MSE or tendency of MSE explained by horizontal advection terms. So, and this is zonal and meridional advection terms. So you can see that horizontal advection terms dominate the moistening and drying to the east and west of the MJO moisture blob. And then if I go back one slide, here you can see the mean state moisture gradient and perturbation wind. And the way it works is, so when you have enhanced convection in the eastern Indian Ocean, like today, and when you have suppressed convection in the western Pacific, this is the setup that gives you a nice coherent eastward propagation of the MJO through the maritime continent. And on the top right, I show the lower free tropospheric moisture mean state. You see some gradient, right? You see, of course, meridional gradient here, right? And also you see some strong zonal gradient to the south of Indonesia, right here, and to the west of Australia. And go back to this my schematic, enhanced convection here, suppressed convection there. There will be some Kelvin response to enhanced convection, and there will be some Rossby response to this suppressed convection. And this zonal wind anomalies and this meridional wind anomalies, they will act upon this horizontal moisture gradient, move this moist air toward relatively dry regions, so thereby moistening this area when MJO convection is over here. So that is actually what is moving the atmosphere, the MJO eastward. And in equations, you can write those terms like this. Now, it's 2015. There was a project where MJO diabatic heating project where we collected a bunch of different climate model simulations and see how the models behave. And then now conclusions are a little more positive. Well, it's still just 1/4, but it's much better than like 1 out of 14 or 1 out of 20, right? So it seems model simulation performance is overall getting better. And then with this data set, Gonzalez and Jiang showed that the model performance, MJO performance, has some interesting relationship with the mean state moisture pattern. So in the scatter plot here, they calculated maritime continent moisture pattern scale, which is basically pattern correlation between observed or reanalysis moisture and model moisture over this area. So how similar your model mean moisture field is to the reanalysis mean moisture field over this area. And the y-axis is their MJO propagation skill. And they found a correlation skill of about 8.8, which is pretty high. And they argued that mean state moisture pattern really matters. And also, what about CMIP6 models? I mean, the previous modeling study, interconvergence study, they just collected model simulation data set, just opportunity-based. So modeling centers may pick a version that has a good MJO. But for CMIP project, you cannot do that, right? This is a diagram that you can see on PCMDI website. And they calculated one MJO performance metric called east-west power ratio from all CMIP 5 and 6 models. And this is the result. And the black gray is observations. So it's about 2.5, meaning over the MJO band, a spectral power of precipitation is 2.5 times bigger than its corresponding westward propagating signal. That's what this number means. And the different bars are CMIP 5 in blue and CMIP 6 in orange colors. And you can see this is the black, I mean, observed value overall. And these dashed lines are model mean values. So overall, CMIP 6 models are doing better. And if you look at, I mean, the models with this value greater than 2.5, you see a lot more CMIP 6 models than CMIP 5. We have just 3 CMIP 3 models and CMIP 5 models and many more CMIP 6 models. And so it seems MJO simulation performance is kind of going up. And we, my group, this is a paper by Min-Sup An from 2020. We did analysis, MJO analysis using CMIP 5 and CMIP 6 models, and we found overall gain consistent. I mean, it has to be consistent. CMIP 6 models are better simulating the sort of propagation of the MJO. And also, we found systematic changes in the moisture mean state between CMIP 5 and CMIP 6 models. So this is mean column water vapor in boreal wintertime. CMIP 5 again top, CMIP 6 in the middle, and the difference on the bottom. And you see CMIP 6 models are overall, on average, wetter. That's the first conclusion. And also it's wetter where climatologically moisture is highest. So that with that, you can conclude that in CMIP 6 models, the horizontal gradient of moisture is higher than CMIP 5. And that, I'm not showing this here, but it's closer to more realistic, closer to the observations. And with steeper moisture gradient, when MJO heating is over here, you get stronger moistening. This is what contours are showing. So CMIP 6 minus CMIP 5, you have more moistening to the east of MJO convection, and which seem to help better simulate MJO in CMIP 6 models. So you can. This has been always a puzzling question. So convection scheme affects many aspects of the model, right? Convection scheme can affect MJO directly, right? Just by influencing how MJO, like convection, is interacting with larger scale circulation. At the same time, convection scheme can also affect the mean state. through other processes. So isolating the effect of convection scheme on the MJO is kind of not an easy job. And in 2020, we grabbed a large ensemble CESM2 large ensemble experiment, just one model, okay? Convection scheme is the same for all simulations in this case. And we, using this massive simulation data set, we picked a period, 20-year period, in which MJO eastward propagation is stronger. We picked 10 of those, and also we picked 10, 20-year period segments in which MJO eastward propagation is weaker. And this is the composite in, like, we call it high MC. MC means propagation through the maritime continent. And then we found that if you look at the mean state difference between this stronger MJO and weaker MJO 20-year segments, the meridional moisture gradient is much steeper in the period in which MJO eastward propagation is stronger. So here we demonstrated that the mean state. So when you change convection scheme, it changes your mean state. So your MJO is better. And it's hard to say whether it's just through the mean state or it's through the direct effect of convection scheme on MJO, right? But in this study, by using just one model, convection scheme is not changing. But through some internal variability, the mean state changes with some low frequency period variability. And with that, MJO propagation characteristics are systematically affected. So we demonstrate this link. Now, if I have time, I want to talk a little bit about a few remaining questions. The remaining question one, I mean, it's a long-standing question, like since like 50s, maybe earlier than that. How does deep convection in the tropics interact with the larger scale circulation? I mean, just to put it in some context, you know, I mean, Xu Guang probably talked about his model last week. These are two moisture mode theories, recent moisture mode theory models for the MJO, and they are using somewhat different their convection scheme. I mean, if you call it. So in Xu Guang's model, precipitation is function of only moisture. But in another paper, Fayez Ahmed, in their model, in his model, precipitation is a function of moisture as well as temperature. And the sensitivity to temperature in his model is actually higher than the sensitivity to moisture. So we still are lacking the understanding of how convection is modulated within the MJO. So different theoretical models are using two very different ways of representing precipitation in their models. Remaining question two, what sets the horizontal moisture gradient in observations and models? Yes, this is climatological December precipitable water field from this website. They're using a bunch of microwave-based satellite retrievals. I have emphasized the meridional gradient here and zonal gradient here. In the current climate, why should that be that value precisely? I don't think we have a theory for that. And again, in these two models, moisture gradient, they are, to my knowledge, they are the only two models that explicitly have meridional moisture advection. I mean, my model also has one, but with this representation of mean moisture gradient, their equation PDE becomes like 8th order, and you cannot anymore solve things analytically, and they use some solvers in MATLAB or Mathematica. But anyway, I mean, there's this one of the key parameters of their MJO model is this meridional gradient of the reference moisture, and they grab it from observations, and I don't think we have a theory for that gradient value. And so if your model underestimate this gradient, we have no idea why that should be the case. So that's something we need to work on, I think. And I didn't really talk about the QBO MJO coupling in my talk, but I mean, one of the most interesting recent findings about the MJO is the very strong observed QBO MJO coupling, and it seems no global climate models seem to able to simulate this coupling. And on one hand, it may suggest models are still too poor to get it right. On the other hand, maybe the observed coupling is out of coincidence or something like that. Well, it's been almost 50 minutes, and these are the these are the sentences that I already have presented, and I'm gonna just conclude my presentation with this final sentence. The MJO modeling has been and will be an integrated effort toward a better simulation of, and eventually toward a full understanding of the MJO. And you can replace MJO in this sentence with any other phenomenon. Okay, I'll stop here and take any questions. Thank you very much.
Thank you, Daehyun. We have plenty of time for questions.
Hi, Daehyun, can you hear me? This is Sombrito from.
Yes, yeah.
Yeah.
I can hear you. Yeah.
Yeah. So if you go to the Soberlin-Maloney kind of MJO theory, then mostly it's like the convection, it's the Gilles response, and the convection is moving eastward because of some process, and the Gilles response is just adjusting to it, and that is how the whole thing moves. But if you look at you have talked here, shown the Hayashi and Ito, so there they probably used some stretching kind of argument, and
Yes.
also in the Ahmed's paper, where they are showing the counter propagating, eastward propagating Rossby-Wave kind of thing.
Yeah.
So there also the vorticity understanding matters more. So what is your views about, I mean, theoretical understanding, then whether it's just the convection and it's a Gilles response is just moving eastward, or it's kind of vorticity dynamics that is in a way, I mean, it's self-adjusting.
Very nice question. So okay, let me go to, I don't have to, yeah, this one. If you ask me, I will say it's the center of the dynamics is moisture anomalies, and like vorticity field, for example, kind of follows. And you know this, but if you ask the others, the authors of the other papers, they may say something else. Well, I have two, I mean, no. One thing that I learned recently was you train a machine learning model, okay? You give like different atmospheric fields to the model, fields of today, and then let them predict MJO index like 10 days, 15 days, 20 days after today. Then the model does a pretty good job. I mean, in a recent paper, one of my papers, our model had like 25 days of skill, which is comparable to the operational S2S model hindcache datasets. And then you remove one variable at a time and see how your skill goes down. And we saw the largest skill drop when moisture field is dropped. meaning you just make moisture anomaly in your initial condition to be 0. You can do the same thing with wind field, but then the effect is not as big as when you remove moisture anomalies. What it suggests to me is the the atmosphere always, I mean, one way of thinking about things happening in the atmosphere is always trying to be in some balance, right? So you cannot change one thing and not change the other. I mean, in the real atmosphere, and things are always correlated. So it's kind of difficult to say what is actually driving something. But my simple experiment with machine learning prediction experiment, it kind of suggests to me the predictability comes mostly from moisture field, and other fields are adjusting to the moisture field. Moisture evolution, it's slow, given that in this budget, the dominant balance is between precipitation and vertical convection. It's always the case when there's convection, and as a result, the residual is not that big, and so the advective process is a slow process, and so I have reason to believe that moisture field is driving MJO dynamics, but I cannot really reject the other arguments that like vorticity, it's essentially vorticity fields that MJO is, and to put it another way, I mean, our observations, the observations and knowledge we have now, it cannot constrain the idea enough so that we just, it's open to different ideas, I think, with what we have. That's, I don't know if I answered your question or not.
Yeah, so I can understand that moisture is fundamental. There is no question about it. But the point I was confused about whether it's a kind of Gilles response that is moving with the moisture anomaly, or it's a coupling between moisture and vorticity. And I mean, the way Sobel thought in his 2001 paper, that how moisture can itself generate vorticity, and vorticity is generating again some advection, and moisture field is changing, or it's just the Gilles response that is, I mean, atmosphere is responding with the moisture in a passive way.
Again, I mean, if you ask me, then I would say the simple Gilles response following moisture field, that's enough. But I mean, to make that argument, you have to make simplifications like dropping tendencies in momentum and temperature equations. And this recent models of Shuguang's and Faya's, they kept all the tendencies and solved 8th order PDE and got some solutions. And they I mean, our models also have problems and their models have some problems. So at this point, I think it's hard to say definitely which way is the more accurate way of describing the MJO. I don't know. Yeah, sorry.
Yeah, thanks, Daehyun. There's one more question in the back.
Hi, yeah, this is Adrian Tompkins.
Hi, Adrian.
Nice summary and presentation and review. I really enjoyed it.
Thank you.
I wanted to come back to the point you made about the mean state. You showed the very nice results where the of the improvement of the mean state gave a stronger signal. And I think to someone watching this talk, it's very easy to get the impression that the two things, improved mean state and improved MJO, kind of go hand in hand. That if you make a change that improves the MJO, you'll also get an improved mean state, or vice versa, that you make a change that improves the mean state, you get a better MJO. And of course, in reality, it's not always like that.
Yes.
It reminded me of my time, back at ESMWF, we knew at the time that making the convection scheme more sensitive to moisture gave us a better MJO.
Right.
But the problem was, if we did that, it kind of, rather than just moving the convection scheme around, it actually suppressed it, and then you'd get some grid point storms. It would mess up the scores. It would make it more noisy. It would also deteriorate our mean state. So I was just wondering, I mean, I presume that the part of the reason why progress has been, not immediate with the climate models also is this fact that probably, people making changes to the convection scheme may improve the MJO, but that at the price of actually deteriorating the mean state. So I was just, in your opinion, do you think we should put more emphasis on the wave dynamics in the climate models, perhaps sometimes at the expense of the mean state? Because I have the feeling that I've not worked too much on CMIP model development, more on the forecasting models, but I presume that the kind of mean state is the thing that they really target the most. Do you think that we should be putting more emphasis when we make our new CMIP generations to actually try and get closer to the different various aspects of the dynamics, even at the cost of, should we say, the mean state of the model? Would that actually get a model that's more?
I don't think we have to like give up the mean state to better study the waves. I mean, we atmospheric scientists, we tend to see things through the lens of linear perturbation theory, right? And when you do that, mean state kind of governs everything, like Barclaynicity and so if you give up the mean state, I don't think that's the right way to go. And yes, what you described is sometimes called entrainment dilemma. That's how Brian Mapes called, or MJO mean state trade-off. If you make your convection scheme too sensitive to moisture, then you suppress convection too much, and you don't get convection that reaches to the tropopause. So your tropopause goes a little bit down, and it affects Hadley circulation and everything. And so in the paper that I didn't mention today, we found that the parameterization of organization, mesoscale organization, you need some more, how to put it, more variability in the depth of convection and strength of convection. So with just one knob, for example, entrainment rate, it's just you overall goes higher, and then whenever there's some instability, you fire convection to the tropopause and deep, and then your precipitation pattern follows SST pattern. Then it gives you a very good mean state, but you lose all the variability. When you tune up entrainment rate, then convection weakens overall, and then this large scale condensation scheme kind of dominates, and it increases variability in all time scales, but also it degrades mean state. So with this organization scheme, you develop this tropopause deep precipitating convection only in some limited amount of time and space when things are when conditions are satisfied, and this mesoscale organization doesn't last too much. In the specific convection scheme that we used Unicon developed by Sung-Soo Park, and that helped both kind of MJO variability and also the mean state. So to go back to your question, I think we as a community try to find a way to keep the main state and make variability better, and study the variability with the better mean state. Yeah.
Thank you.
Thanks.
One last question in the back.
Yeah, nice presentation, sir.
Thank you.
I'm Sripati from NIT Rourkela. Sir, what is the role of ANI waves, mixed Rossby waves during the MJO propagation? In the nowadays, like QPO and MJO both are in the increment of MJOs, QPO oscillations also impacting. So how the ANI waves also ANI waves impacting, sir?
So there has been, especially after this Daehyun's Yang and Ingersoll study, which is saying the MJO is a result of the interference between eastward propagating and westward propagating gravity waves. There's been some, and also in the context of, okay, MJO gives you a large envelope of, within that envelope, the environment is more favorable for convection to develop. Will you get some systematic changes in the frequency and intensity of those high frequency equatorial waves, or will you get some random waves? Meaning in some MJ event, you get just 2 Kelvin waves. In other MJ events, you get mixed Ross gravity waves. In another one, something else. And so Juliana Diaz and Georgi Kalaris, they have analyzed observations with this question, and what they found was it's sort of random, right? MJO just gives you a condition that's favorable for convection over a large domain, and then it's exactly what type of wave develops within that envelope. It's not systematic at all. That was their conclusion. But I know a Japanese guy, Daisuke, he, in his PhD thesis, he came up with this hypothesis that mixed Ross gravity waves are key for the MJO initiation in the Indian Ocean. And he argued it's systematic to many MJO events. But for the propagation, I don't think we have seen any systematic relationship between MJO and other types of convective couple of waves.
Thank you, sir.
Thank you.
Hi, Daehyun.
Yes.
This is Pratiksha from IISc Pune. What do you think, can the MJO influence the mean meridional circulation, especially say in regional scales, if we take the regional Hadley cells? So can it affect those mean meridional circulations through either its convection or circulation component?
With the current way of thinking things, I'm talking about the linear perturbation theory. It's hard to say the study how MJO influences the mean state. Specifically, we first assume that there's a mean state, right? And then consider MJO as perturbations to the mean state. And by definition, right, your mean state doesn't change. But so when I was working on a paper, I didn't mention it today, which argues that mean state moisture field matters to the MJO. One of the reviewers asked a question along the line of the thoughts that you just had. Well, maybe MJO have impacted mean state moisture, right? So that's why you have different MJO moisture. So what we did was, so specifically, we compared years with steeper moisture gradient and years with less steeper moisture gradient, and compared MJO activity, and we found stronger MJO activity with years with steeper moisture gradient. And then in those years, we took out all days with strong MJO, with RMM amplitude greater than 1. So we just retained days without MJO, and then constructed the mean field, and the mean field looked almost the same. So with that, we concluded MJO does not systematically affect the mean state. Yeah.
Thanks.
Thank you.
Yeah. Thanks a lot, Daehyun, for this very nice talk, giving historical perspective as well as the cutting edge knowledge in this field. Let's thank Daehyun again.
Thank you.